So yeah, assuming taking a step back a little bit, assuming that artificial general intelligence is the end goal with embodiment as well, let's say, do you think that both kind of, let's say, fully end-to-end research and also research which combines learning with things we already do know about, such as motion planning, physics, and geometry, do you think kind of both of these tracks are necessary? And what unique purposes do you think these two styles of research serve in the journey towards AGI? And just to give some examples, I would say, for example, the perceiver.io, a new transformer architecture, is one example of something that's kind of actually taking away some of the inductive bias and from the graph. For example, they solve optimal flow with really very little assumptions of the problem at hand, whereas alternatives such as PwCnet has a cost volume embedded in the forward pass. That's kind of one example of taking away things that we do know and kind of letting the data speak for itself. Do you think that track of research, and that includes then end-to-end RL, do you think they have a part to play? Maybe if that kind of shows its real benefit in 50 years or 100 years, maybe when data resources explode, maybe actually we can kind of keep taking back our prior knowledge from the solution. So what do you think those two tracks of research have to offer, and do they complement each other in some way?
Well, I certainly think both are important. And I think when you're working in AI and robotics, you have to decide at what point in the future are you optimizing your research towards. And some people will say, well, I want to do research such that it goes into commercial products in the next 5 years. And some people will say, I'm aiming for human level AGI, even if that's 50 years or 100 years or even further away.
Yeah.
And so I think in the former case, then you probably would use a lot more modeling and engineering and using methods that we know work now. In the latter case, you would probably be trying to remove some of that engineering and allow robots to learn that behavior. Because if you have the more kind of inductive biases or the more modularization you have, then the harder it is to overcome those asymptotically. Whereas if you can use learning, that will automatically optimize for the tasks that you really care about. Then hopefully with more and more data, which should be possible in the long term, you would overcome those biases. So I think both are important for impact in society. But in terms of really achieving AGI, it's really difficult to know. It goes back to the question we were talking about before, but it's really difficult to know what that thing is that the end-to-end system should be optimizing for. And what do we really mean by end-to-end? Do we mean end-to-end control, where observations are directly mapped to actions? I think that's perfectly reasonable, and we understand what that means. But it might fit in with a broader pipeline that, for example, would choose which controller to execute at any one time.
Yeah.
Or do we mean actually learning from a pure reward signal like survival? And in that case, again, we'd have to be sort of somehow replicating evolution. I don't know whether we would really ever have the amount of data or compute to do that.
Yeah, I guess when I use it, I guess more just kind of actually what I should instead say is just kind of the removal of inductive biases of any form, really. Because I guess you can, of course, have an end-to-end trained system which does map from observations to actions, but your computation graph is heavily designed and the gradients you're passing go through something that's been carefully constructed. So that would still, although it's trained end-to-end, not be necessarily what I mean when I say end-to-end. I kind of just mean removing inductive biases, whether that be through the loss function, through the computation graph, or from any modularization of your system at all. But that includes then the reward function as well, I guess. So I guess the complete end of that spectrum would be something that is a completely structureless network optimizing something as simple as an evolutionary algorithm. That's kind of the extreme on all fronts of an end-to-end approach. So kind of exactly what you're saying, I would say.
It's very difficult to say what a system would be without any inductive biases, because you can start off saying that, a convolutional neural network has inductive biases with the convolution, so let's change that to a fully connected net. network. And then you could say, well, okay, yes, but there's, we've got activation functions in there that we optimize for, and we've got, there's maths in that neural network that we've specifically designed to work. So if you then remove that, I don't really know what you would. I guess you would end up with just data points, and I don't know. I don't really know what that would look like if you removed all inductive biases. It's I guess nearest neighbor in the original feature space might be the closest thing, but then you'd have to do some optimization over those nearest neighbors or something. I'm not quite sure how that would look.
I guess it wouldn't be about kind of removing all inductive bias, I guess, but just kind of domain specific inductive biases. For example, like a convolution is like vision specific inductive bias. And I guess also I'm kind of talking about what transformers are doing and stuff, where actually one network can kind of fit all, and there is inductive bias there, and the kind of processing that happens, it's obviously very parallelized and very non-linear, and these are things that we expect the function to be, but it kind of is, I guess, removing the ties to any one domain or task as much as possible. But I guess, it's just kind of, I think, you've already answered the question in so much as, both these tracks of research, I think as well are very important and serve different purposes, whereby the one that really says, let's assume nothing and let's just see what we can do with bigger compute and bigger data sets and take all of it away, that is very scalable if the future does indeed lend us hugely more parallel compute than we have today. Then these are very great methods to really scale with that increase. But as you say, if you want to kind of get robots in the home in 10 years time, maybe your best bet isn't to kind of go down that track. I wonder if Ronnie want to weigh in a bit. Oh, you're on mute, Ronnie.
Yeah. So I think like another way to view it as well is kind of like for humans, like you can show someone an equation or like show someone an algorithm and they will be able to use it. They don't have to discover it from scratch by like learning or like exploring. So I think like another way to see these inductive biases is kind of like a way to actually kind of show these models how to do specific things without them having to discover it. It's not exactly the same, I think, as the current biological kind of setup, because we kind of embed these relations into the models at the moment. But maybe in the future there could be a way, sort of, a way to actually like show neural networks an equation, and they could kind of incorporate that into their computation or something. I guess it kind of goes to meta learning or like those kind of things, but I just think like you can fit these handcrafted kind of knowledge and inductive biases into neural networks without having to say like, oh, you have to go end to end or you have to go handcrafted. Like I think there is a synergy there that people kind of miss.
But do you not then? My question will be: do you not always, like, even if it's on a small scale, do you not always slightly constrain the network by adding this inductive bias? Because, for example, convolutions are incredibly useful and like revolutionized vision. I mean, that was kind of what enabled the kind of next wave of deep learning and everything with AlexNet and so on. But and then with transformers now, actually, you can beat that performance or at least get very close and actually, overcome it without any of that. So even though they're very, very good, maybe. I mean, the trend seems to be, at least so far, that when you have enough data and compute, actually anything we can design, normally there's something that's a bit more optimal and can actually kind of find connections in a more optimal way than we can hand design. So do you think do you think it's fundamental that adding inductive biases comes with it at least a small amount of constraint on the kind of way that it can learn an optimal function?
So I think it doesn't necessarily have to add a constraint, because for example, you could have parallel channels where you add in a handcrafted kind of computation, and then you have another, channel working alongside that doing like a learned computation, and then they fused afterwards. So in the case of like, the cost volume or, some modules in computer vision, those don't have to be done as a single, kind of like bottleneck in the network. You can do them in parallel. But the best way, obviously, to integrate those with the general network structure is not really that obvious. But I think that the key thing, kind of, or the way I always just see it is if you're telling someone, or if you're showing someone an equation, or you're showing them some relation, for example, like how to solve, like some x squared plus y squared equals 3, or like Pythagoras' theorem or something like that. They don't discover that on their own. They just see that relation or that equation, and then they use it in their work. So yeah, I just think there's kind of a way to kind of fuse this handcraft knowledge and the neural networks.
I guess with this sort of this analogy with like human learning across generations. These equations that you're talking about are often just true, and it's not like, it's very rare that scientists in the past have come up with equations that just simply are proved them to be false, right? They're either pure mathematics where a proof is made and it's, suddenly that is just true, and it's because it's been proved, or it's more kind of empirical, like Newton's laws, and it's just fundamental, and that's just how the world is. And so it's very, very rare that these equations are later proved to be false. So it's quite difficult, I guess, to come up with the equivalent with AI, where we actually know that this equation that we are giving the robot is pure, and there isn't a better version of that. And so usually these inductive biases are probably not optimal, and they're somewhat, they're better than not having these biases in there because they speed up learning, but they may not be optimal. So I guess the equivalent would be like a field of science where actually, we use previous scientists' knowledge to update our understanding of that field over time, which I'm sure, that happens in computer science, I guess, but more on a kind of conceptual level. So maybe we could give robots approximations of what we think are good inductive biases, and then the robots and the AI can adapt those over time and actually perfect them towards the purer goal that they're trying to achieve.
I think that sounds very interesting, actually. One thing I would just add to that, actually, because it made me think, is that I guess, as you're saying, like in learning, we very rarely have these kind of perfect inductive biases that can just be easily added in. And I guess even when we do, for example, because we have physics, like the laws of physics need to be adhered to, and maybe we should embed that into the model. But actually, if what we want is an efficient control system that can take observations and select their actions, Sergey Levin gives this very clear example where when you're catching a ball or something, you could actually like try to model the 3D position of the ball, model its acceleration and so on, and plan yourself to be there at the right time. But actually, for example, you then what you might then do is just keep it in your horizon at the right height. So as you're kind of running to catch it, you just keep it in your eye line at a certain angle, and then you arrive at the right place at the right time to catch the ball. And so I guess, there's lots of cases where you could solve many problems, including control problems, by modeling everything perfectly. But to actually get a very responsive closed loop controller that's like optimal in terms of response time, for example, you might not need to kind of model these things. So I guess that is, as you're saying, kind of, it's not clear what inductive biases we even want. Even if we have them, it's not clear that they're optimal with what we actually care about in the computation graph.
I certainly think inductive biases in terms of physics, I don't think humans actually have very good physics models in terms of precise predictions of where things will be. I think our models are much more about what happens when I apply this primitive skill to the world. Conceptually, what will the result be in terms of the relative poses of objects after applying this skill. So, you know, if I pick up I don't know, it's a carton of milk and pour it into a cup, the milk will go out of the carton. But I don't know exactly how much, and I'm not reasoning about it in terms of volumes and velocities. I just know that when I do this thing, this other thing will emerge, and they're kind of concepts rather than physical states of the world. And we have models at that level that we are able to apply very, very broadly. And I think that's the level probably where the inductive bias should come in. We should be saying, you know, for example, you could say, well, let's learn 1,000 different primitive skills, and then let's learn and let's learn a representation of states that is at a more higher sort of symbolic level. And let's learn to combine those skills with those symbolic states to be able to then build a model. That framework itself is the inductive bias rather than the actual low level modeling of dynamics. So I think we can, you know, that's probably the level that I see for, I don't know, kind of medium term robot learning, beyond just sort of engineering everything, but probably before we actually reach AGI.
That makes a lot of sense.